Hey, good afternoon, everyone. Welcome to our PIES webinar. PIES here stands for the Physics, Innovation, and Exploration series. So glad you can join us this afternoon. Let me just admit. Okay, yes. And so for today, we have the great honor and privilege of Miss Vera Puah, right, who is one of our Singapore young physicists, to share on her project on swirling balls, right? The mechanics of swirling balls. It's a really interesting topic, and I can't wait to hear more. Allow me to stop my share so that she can then share her slides.
Right, thank you.
Okay, great. Thanks, Vera. Take it away.
All right. So, good afternoon, everyone. I'm Vera, and today I'll be walking you through the physics of this simple phenomenon of swirling balls. So, you can see in this video here, this is actually a demo of the phenomenon, and there's actually quite an interesting crystalline structure you observe here because of the way that circle packing occurs. So, if we take a look at a video of the phenomenon, so you can see very clearly that if you trace out like one of the specific ball's motions, for this ball specifically, it moves in a counterclockwise direction around the container. And so something interesting about this is that it's actually following the direction of the container, which is moving clockwise as well. So here we would term it co-rotation since they're moving in the same direction. Now we can look at another motion of this ball as well. So we can trace this exact same path as the container moves still in the same direction. However, now it's in the opposite direction. So now it's moving in a counterclockwise direction. And the container is moving in a clockwise direction, which makes us term this counter rotation. So some questions that are raised here. So the first obvious question is that what causes the balls to move in the direction opposite to the motion of the container? So another natural question about this is also what factors affect the direction of rotation, whether it goes clockwise or counterclockwise. So some things we would think about are, for example, what forces are acting on the balls? Is there something about these forces that is changing the direction of motion? And it seems to be affected by the number of balls. As we've seen in the previous two videos, the only thing that was changed was not really how fast the balls were moving, but more of the number of balls. And could this be caused by the interactions that are going through, like between the balls? And other than the number of balls, could there be something else going on? For example, if I move the container faster, could this somehow change the direction of motion? So here are some factors that we will start to look at. I've listed them all out here. And the first one just covers the ball parameters, while the second covers the parameters of the moving container, while the third one covers the parameters of the container itself. But we could look at the radius of container and the number of balls as sort of a similar kind of thing going on, because all it's really telling you is it's kind of giving you information about the packing fraction of the balls in the container. And as for the static and kinetic friction coefficients, these would have to do with a lot of the interactions between the balls as well as between the balls and the walls, which could be interesting to investigate. So now that I've talked about this, let's actually look at the ball motion. So in the co-rotating case I showed you earlier, what I did was to actually track the motion of all the balls. And as you can see here, it looks pretty messy. It doesn't really look like there's any clear pattern. However, when I track this exact same thing for counter rotation, we notice really, really nice concentric rings. Now, this seems pretty natural given the fact that I've just told you that when I add more balls, the thing seems to counter rotate. And this would prevent the balls from moving a lot, which makes sense that there's this sort of regular pattern going on. But what more can we learn from this? So moving on to a qualitative model of this phenomenon. So the first thing I would like to introduce is the centrifugal force. So we notice that a lot of the time in this problem, we're talking about the motion of the balls with respect to the container. So it would be really, really nice if we could look at this problem from the frame of the container. So you know that there's this centripetal force that's driving the container in circular motion. But in the frame of the container, it appears as if there should not be any force acting on the container, since the container is well, at rest with respect to itself. But if there's a centripetal force, how can there be no net force acting on the container? So the answer to this, seeming like something that seems like a paradox, is that there's actually a centrifugal force. So from the frame of the container, there is this additional fictitious force that would not exist in the regular lab frame, or a frame that's basically observing the container at rest. Now, this centrifugal force is what we'll refer to later when we're talking about what drives the motion of the balls throughout the container. So in the frame of the container, if you were to have your ball to roll without slipping, you would have some sort of a centrifugal force acting on it as well, since it's moving within the frame of the container. So let's say it has a certain velocity. The centrifugal force, what it's going to do is it's going to drive the ball in a circle, because the direction of the centrifugal force keeps changing with the container's motion, and the ball is just going to be pushed around the container. So if we look at an actual video of this happening, we see some sort of gyrating motion where the ball moves in a somewhat circular motion. However, we see that there's a lot of sliding happening, and it sometimes collides with the wall of the container. And this is where we have to sort of take into account the frictional, like whether friction is actually strong enough to maintain the motion of the ball. And if not, how are we going to account for these collisions? So since we're interested in the direction of the motion, all we need to do is really look at what happens if the ball collides with the wall of the container. And due to the momentum of the ball, it rebounds in the opposite direction of its initial velocity, but this keeps it going in the exact same direction. If you talk about whether it's going clockwise or counterclockwise, it would not reverse and go counterclockwise if it's originally traveling in a clockwise motion. And with a few balls, we notice that now there's sort of like interactions between these balls. However, the balls are quite far apart, so we can treat them as being analogous to a fluid. So in the frame of the container, if we look at the ball-ball collisions, which is something new that we haven't looked at yet, we notice that the same thing about the momentum actually does apply here. So what happens is that the rotation is actually slowed down because the balls sort of inhibit the motion of each other. However, this would not be sufficient to reverse its direction completely, because the total momentum of the balls would still follow the same sort of pattern, and hence collectively the balls would still move in a clockwise direction. Now, if we were to look closer at the spin of the balls, something interesting that's happening here is that because the ball's spin is a lot more limited when there are more balls, with counter rotation, the balls are not given as much freedom to spin in full revolutions. And this is interesting because it also affects how the balls are rolling around. And this is also part of the qualitative behavior of the balls in counter rotation, whether or not there are many balls or not. So now let's look at the case with many balls first. The motion of each ball is constrained by the other balls, as we've already mentioned. And if we looked at the balls as sort of like a deformable solid, we can actually use this analogy to an actual pancake, which is probably where the name of this problem comes from. So over here, we have this large pancake, and we look at it as a sort of object on which friction is acting. And so this frictional force actually creates a torque on this giant pancake. This results in a rotation in the opposite direction of the rotation of the motion of the center of mass of the container. And this torque is what drives the counter rotation. In fact, we can even confirm that this counter rotation is driven by friction. I've added a non-slip coating to the first container, and we can watch to see what happens to the ball's motion. This video doesn't seem to autoplay. The video seems to not be working, but so I've done the exact same thing with lubricated balls, and basically what happens is that you see co-rotation, whereas with the non-lubricated balls you see counter-rotation. So I've essentially confirmed this experimentally, and I think something that's interesting is also that in the case of lubricated balls, this also affects the friction between the balls. However, it's kind of difficult to change the friction between balls, while it's much easier to just change the friction between the balls and the wall. Now, with increasing shaking frequency, we have a similar thing going on in terms of how much freedom the balls themselves have to sort of spin around or move around. So over here, the magnitude of the centrifugal force increases. So what happens is that the balls are driven in much bigger paths because they have a lot more energy. And along with what I mentioned earlier about the spin of the balls being restricted when the ball number is very high, now since a lot of energy is contained with for each ball, it has a lot more it has a lot more room to spin around, and hence it can just easily follow the motion of the container. So I've traced out the paths, and as you can see in the first video, for the ball that's being traced, it sort of stops around at the middle of its circular path, whereas for the second one, it basically completes full circular paths each time. So when you increase shaking frequency and you consider a single ball, its translational motion is going to follow the shaker motion. And it will slide along the sides of the container and keep moving in the same direction. So now, moving on to a more quantitative model of what's been discussed earlier. So let's first take a look at this free body diagram. So as we've established earlier, there is a centrifugal force acting on the ball. And we also have the frictional force acting along the plane of the container. So what this tells us is that we can write down Newton's second law in the vectorial form so that we can get the vectorial acceleration of the ball. And note that the directions of the vectors here are just for illustration, and they can basically be in any direction at any time. And if we look at the side view, we want to look at how the ball is spinning. So we also do the exact same thing with the top analog of Newton's second law, and this is how we obtain the angular acceleration for the rolling ball. When it comes to the collisions, there are two collisions we need to take note of: the ball with the wall and the ball with another ball. So for the collisions with the wall, we can compute the impulses as those being due to the normal force, friction, as well as friction in the other along the ground. Now we write down a bunch of equations. The first one would be the conservation of momentum, because we want to compute what the impulses actually do to the ball. And then after that, we take the angular momentum equation as well as the torque equations to actually find the equations that are governing the motion of the ball itself. And we also use the coefficient of restitution to account for whatever energy loss is happening during this collision with the wall. We also characterize this coefficient of restitution by taking a video of the ball colliding with the wall and looking at the final velocity. Now, for the collisions between balls, the equations used are kind of similar, but now it's just two balls interacting. So previously the wall was fixed, but now we have to account for both the velocities, and this is done by writing the two conservation of momentum equations over here, where you have the normal force and the frictional force. And then we look at the torque equations, where you incorporate these impulses into the exact same equations that we've had earlier, and essentially just use L equals to I omega. Now, we also use the same coefficient of restitution equations from earlier, except now it's for the balls, and also compute the normal impulse using the equation below. However, in reality, there's some deformation occurring when the balls collide, and this is something that is investigated in more detail in solid mechanics. So for this report, I will be using the Hertzian contact model. So based off the overlapping area over here, we compute the normal force using this equation. So it may look complicated, but essentially what it's doing is that there's like a sort of Poisson ratio and also a sort of damping coefficient to sort of describe this compression that's taking place for when the ball collides with the wall. And the Hertzian contact model usually is used for circular objects, but in this case, the wall is basically a circular object of infinite radius.
Yeah, I had a question, Vera. So this equation that you're putting here, the Z subscript n, that is that something that you measure, or it's yeah, how do you get the sort of Z parameter uh, to work in your model?
So the Zn is a sort of compression factor. So like it changes over time, and we have to actually model how much it compresses. So basically what's going on here is that when your ball, like for example, when your ball collides with the wall, the compression will like start to increase and then it will decrease. And this rate of change is also accounted for in this normal force equation. And yeah, it just goes into all of your equations, and eventually you can solve for whatever this compression is based off how much like based off literature, like how much your object will compress.
I see. So you are sort of treating the ball like a spring, elastic kind of spring, where you have a kn that you do you experimentally determine that as well?
Yeah.
The okay, right. And then I see. So by doing using this equation, you sort of model how much normal force is being exerted as the system evolves. Okay,
Yeah.
cool. Thanks.
So we also have this frictional force, which is kind of similar to like the regular frictional force. And from here, we are able to compute the linear and angular acceleration via Newton's second law, since we already know all the forces that are acting on the ball. And so we can do the same thing that we did earlier. Now with two balls, we have almost the same thing, but now the overlapping areas between the two balls. And we have a lot more forces to take care of. So you have that normal force, the frictional force between them. And the normal force is a similar equation as is shown previously. While and from the top view and the side view, you can see that we are able to compute the contact velocities at each of the contact points, and hence we can use this to compute the linear and angular acceleration once again. Now, another thing we have to account for in this model is the sticking and slipping, because the frictional force could be static friction or kinetic friction. So for sticking, we have to calculate the frictional impulse required to maintain a contact velocity of 0. But if this frictional impulse needed is too much, so if it's greater than the maximum frictional impulse that static friction can even provide, it's going to start slipping and transition into kinetic friction. So computationally, we basically have to implement this and check it at every time step to check whether it's sticking or slipping. Now, moving on to experiments. So first of all, experimentally, what I have done is I have placed I've used an orbital shaker and placed a friction mat on top of it to prevent slipping. And then I've placed my Petri dish with steel balls on top of it. So I've got this plastic box and my phone overhead to record a video of the balls. And then I've got the spirit level to make sure that my phone is aligned correctly. So the first thing I've done is to check whether, like previously I've already mentioned that I think that ball wall friction is the main driver of this phenomenon. So I have to check whether this is true in my theoretical predictions as well. And indeed, it seems to slide very, very quickly in the clockwise direction if there's no friction at all. And this is something that's generally good to do when you get any sort of physical expression. It's good to check the limiting cases to sort of get like a reality check as to like whether you're correct or not. So another case I've done is I've basically fully packed the container and checked whether I observe co-rotation or counter-rotation. So as you can see here, both theoretically and experimentally, I've got very, very similar ball paths going on. And I can observe the same thing if I look at lower end as well. The paths of the balls are actually very close, demonstrating good predictive power of the theoretical model. When I lower the shaking frequency, it's also quite similar. And I've also used a larger container to investigate other packing fractions. I've also done the same thing with a larger ball size, as I wanted to try seeing what would happen if I changed the radius. Now I've also plotted a graph of the sort of frequency I need to actually force the balls to co-rotate. So essentially, I've taken this data for two different types of balls. I had steel balls and plastic balls. And as you can see, the error bars here are actually sort of large, and this is due to experimental limitations because the orbital shaker is somewhat unstable at higher RPM. And so what happens is that it actually does fluctuate between a range of revolutions per minute, and hence, and there's also an interesting trend at the end where the sort of gradient of the graph of the orange points is actually greater than that of the blue points. And in fact, someone actually asked me about this recently, but to be honest, I have no idea why this is the case because it seems that it's not really something that I can predict qualitatively yet. So basically what's happening in this lower region, yeah?
Yeah, so I was I mean I think that's what you just mentioned really interesting. So for these two kinds of balls, you kept everything the same, except maybe I mean including the radius and so on. Is that
Yeah.
probably what you did? Okay, so you found that the orange point being higher than the sort of steel one at high numbers. What at n is the number of balls in the container,
Yeah.
I guess. Okay, so that means when it's very packed you need to spin it faster. Uh, okay, generally speaking, I guess that the graph trends upwards, lah, right? So when it's more packed, you need to spin it faster for it to co-rotate, right? And it seemed like when you add the last ball, I guess the last ball is really like from 29 to 30 is like the most you could add is
Yeah.
something like that. Okay, so it happens when it's like fully packed, then the plastic really needed much more um than the steel. Okay, okay. It could be, I don't know. It seems like the plastic maybe sticky, more sticky to the walls or something like that. I don't know. Okay, but yeah,
I
interesting to
think
take
that's
a look.
possible, but yeah,
Okay, cool.
interesting.
Thanks.
So, I mean, preliminarily, the trend here we can sort of explain, given by the fact that there's actually a lower friction between the plastic balls, because the balls are a lot less massive. So we also have like a smaller impulse going on. So the normal force is going to be smaller. And if we look at like the circular paths of these balls, interestingly enough, we can actually see that experimentally, the balls actually do trace out circular patterns as well. So another parameter we want to look at is the average rate at which the ball actually makes a sort of revolution around the container. So what I've done is essentially looked at the angle that it traverses over a certain period of time and then taken the time average. So I have this graph for the average omega ball for varying n. And interestingly enough, there's also another trend going on here where the points consistently lie above the line. And I believe that this could be due to some inaccuracies in the characterization of the friction, because the experiment seems to be very, very sensitive to the values of this friction. And it's also not very easy to get these values because, first of all, the container is quite small, so it's a bit limited. And second of all, I also think another issue could be the friction between balls is very, very hard to characterize because we don't really have like a giant steel slat. So it's a lot easier to just use literature values. So over here, what we can see is that there's a transition from co to counter rotating as it goes down. And as it goes up, the average omega ball actually decreases again because the ball motion is very restricted. So there's a lot, the distance that it can travel is much less. We also see this graph for varying frequency. And again, there's also the same trend of the balls lying above the line. So at the start, as the balls get shaken faster, they start to move a greater distance around the container. And as you move up again, you see it start to transition from counter to co-rotating, where the direction starts to reverse. And after that, it just continues going up. So now we can also look at a phase plot for when it co-rotates and when it counter-rotates. And as we can see, there's this sort of transition line that we can somewhat predict, and the predictions seem to be better for a higher number of balls. And we can also see the same trend that we've predicted earlier, that the higher the number of balls, the higher the revolutions per minute needed to induce co-rotation. And I think one possible reason why the predictions are a lot better at a higher number of balls is also because the balls the balls are very limited, so the distance that it can travel, like it won't deviate that much that when we predict it theoretically versus experimentally. Yeah.
Okay, so can I check just to confirm my understanding of this plot? All the various dots are all your experiments, right? That means every single time I see a dot here, you have actually said let's say done an experiment with 10 balls at 200
Yeah.
revolution per second and repeated for 190, 180, 170, 160 and
Yeah.
so on. Right. And then that line separating the green region, the green shaded region and the red shaded region, that will be your theoretical or
Yep.
simulation line that you get, right? And it's really, I guess your theory is you basically put your theory into some kind of code, then you run the code, and then it
Mm.
generates the motions, and from that sort of simulation, you figure out whether it is co-rotating or counter-rotating. Is that how? Okay, great. Thank you so much.
So what I've done after this is actually some like additional insight into the problem, I guess. Because what I've done here is I've packed it to a certain specific number where the balls actually form sort of different rings. And something interesting here is that if you look at the inner ring with only four balls, the innermost ring, you can actually see it rotating. And the shape of it actually stays relatively consistent due to the way the balls pack. But what's more interesting is the fact that you can see like a sort of higher level of, or like an additional level of this pancake motion happening because the inner ring is actually rotating in the opposite direction of the blue ring because of the exact same sort of pancake phenomenon going on, creating a torque in the opposite direction. So now for some further insights. So this was initially a random idea I had to do because it seemed like something that would be interesting. So, interestingly, during the actual OIPT fight, I was asked by the jurors whether I had investigated non-uniform ball radii, and I think, like, I guess I was kind of lucky that I did think of trying it beforehand. So I think actually this is quite interesting from a mathematical point of view because what this really changes is the geometry of the system. I mean, physically we could always put in the same parameters and still compute everything, but it would kind of be a black box. So geometrically, this is interesting because this allows us to maybe fit a lot more of the volume and basically like pack the circles to like the most optimal sort of packing. And this could be interesting because this could really change like how well it co-rotates or counter-rotates. Another interesting thing I tried was to use a bunch of different materials simultaneously. And I guess something interesting about this is that for the metal balls, it seems to be like a lot more momentum transfer because when we look at non-uniform materials, one thing we have to take into account is the differing masses of the balls. And for the last video, you can really see like each time one of the steel balls goes around, it sort of propels the next sort of outer ring of steel balls to continue moving forward, whereas you don't really see as much of that with the plastic balls. And when you put them both together, you can see some sort of um, I guess some sort of behavior between the steel balls sort of clumping together and the plastic balls mostly staying on the outside. So in summary, what I've done with my theoretical model, I've explained the cause of counter-rotation in terms of the ball-wall friction, and I've solved the ball-wall and ball-ball collisions, first talking about coefficient of restitution, but then using Hertzian contact to more accurately model the collisions. Then I've also quantitatively predicted the full motion of every ball, and experimentally, I've investigated the transition from the co-rotation regime to the counter-rotating regime, and obtained agreement between the theoretical and experimental ball motion, while also varying things like the ball material, number of balls, and revolutions per minute of the container. So here are my references. Thank you.
Thanks so much, Vera. That was really amazing. Um, maybe I could start off with some questions and then the rest can add on. I guess probably easiest if we go back to the result. I guess going backwards. Okay, maybe the one slide I remember was the one where you said, if you have the blue circle, the red circle and then the blue circle, right? This one. Um, are you saying that, in a scenario where let's say the outermost balls are, what's that, either co-rotating or counter-rotating, then there's an alternating pattern as you go in. Is that sort of what you observe?
Yeah, but this also only happens for certain geometries because of the way like the rings form. Like some of these geometries might not form like actual rings because there might not be enough balls.
Right, right, right. So when it's really quite circular, I guess, then you do have you can actually observe that alternating, like that means if the outermost ones are counter rotating, then the next ring inside is sort of counter that counter and counter all the way in.
Yeah.
Okay, okay, cool. Then I'm really fascinated by sort of like the coding you had to do. I mean, I would imagine that as you put more balls in, the sort of time taken for your algorithm to run probably
Mm.
goes proportional to n. Would it be, or is it more like n squared? I mean, because of all the different interactions that you have to add in. How's the performance
I
of your code like? I mean, so how does it scale with the number of balls?
I think it would be something like n squared, yes, because of like the ball to ball
The
interactions. Yeah.
interactions are right. Okay. Wow. Okay. But it runs relatively quickly. I guess it does it. Was that a
Um,
limitation?
it was one of the problems because it would take like sometimes multiple hours to get like a few runs of like similar data sets.
Okay. 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 But you still managed to get so much data out of
Yeah.
it. That's cool. All right. I remember. Okay, this one. I made a mental note. Slide 41. I can't remember. I had a mental note. I can't remember what exactly the note was. Oh yes. On the right image, was it basic carbon paper that you used? Is it, and then the steel balls like made those lines? Is that what happened?
Actually, what I just did was to use some marker ink to like
Oh,
make
marker
the
ink.
markings and
Okay.
then
Okay.
yeah,
Okay.
and then I just left.
Wait. So the marker ink was on the ball. Wait.
Yeah,
Oh, okay. So some of the balls, like sort of like were painted with marker ink, and then
yeah.
oh, okay, okay. Then they trace out these. Yeah, it's very clear that they trace out these circles. Cool, cool, cool. Okay. Would anyone else have any questions for Vera? Feel free to unmute and ask your questions if any. Yeah, I think there's a lot of richness that probably will take a while for us to absorb. But yeah, it's really, really, really fascinating. So Boon Siong has this question about, any sort of practical applications have you found, or like based on your research, were there people looking at this for particular technological reasons?
So I think an interesting application of this I actually saw was that so initially I was reading some papers and it turns out that this has a similar thing has been investigated before. It's a sort of like foam-like structure in liquid. So this is useful in like a lot of biological I guess experiments because they use like a similar sort of shaker machine that goes in fact the orbital shaker is like a pharmaceutical like device and so like they've done a similar thing with liquids and they've noticed that with the bubbles on top they can actually follow the direction that the liquid is moving or they can go in the opposite direction and I think it's probably somewhat similar to what's being investigated here. And I think another interesting part of this problem is also the fact like how it applies to like granular mechanics because like although the particles we're investigating here are quite large, it might be useful to look at like in the limiting case of making these particles much smaller, how it would affect the motion of these like granular media.
Thanks, Vera. Any other questions? Okay, actually, maybe one question as you're describing that, right? Was when you described briefly that non-uniform balls. So what you were mentioning at that time was that when you have different sizes of the balls, you actually you can actually pack it more tightly. Sort of like fill up the spaces between the big balls. You can have your small balls, and then what was it that you what is there any sort of like a clear finding that you got from that, or it was just like just interesting to watch?
I think we didn't really get any conclusive finding, but it is interesting to watch. And I think another thing, like since I pointed out the sort of like phenomenon with some sort of foam-like structure, it's actually sort of applicable to that because the bubbles in that foam-like structure might not all be of uniform size. So it's actually quite interesting to like look at it as an analogy, I guess.
Okay, I guess bubbles, yeah, bubbles are interesting also because I mean they're sort of like your anti bubble, right? Or so your anti mass, right? Because the bubbles float and so they have the sort of
Yeah.
anti inertial effect. Okay, I think Ronald had a question about the angular speed. Sort of like in terms of the experiments, like how it was measured. I'm guessing that you probably use when you took the video, you probably use a software like Tracker or something like that
Yeah.
to mark it out. Right, right,
Yeah.
right. And then for your simulations, I guess, I mean, you were able to use your simulation to produce a visualization, but I suppose you could also probably pull out a variable that was in the code to then map that out. Okay. Yeah. So Ronald, hope that answers the question. It's okay. This tracking, I suppose it does the auto tracker work, or you do have
No,
sort of.
if I had, yeah.
Wow, wow, wow. That's amazing. That's yeah. Because I can imagine every single time you take a video,
Yeah.
the ball, makes so many dots. I mean, yeah, you have to really trace it. Okay, cool. Any other questions that anyone else has? Okay, I know Jolene came in a bit late, so maybe you skip. Okay, yeah, she's saying friction between the balls. Yes, was it considered? Yeah, so I guess Vera, maybe you could go back to your. Okay, I mean it's a bit intimidating, right? But we go back to your sort of equations and the models. Uh, I guess you probably considered almost everything, right? So Jolene, I think if I were to answer, I mean, and of course Vera should confirm or correct my understanding. She really put in as much of the physics as possible, even up to the deformation of the balls when they hit each other or they hit the container, and then put in all the forces and then run the simulation. So that's my understanding that she really put in every single thing that could matter.
So in the case of like this Hertzian contact model, we also need to like combine it with a slightly different friction model from the usual one because of the deformation. But what we do here is just it's essentially the same thing, but it's a Coulomb friction model. Yeah.
Okay, Coulomb friction model. Okay, I see. That's the F subscript F that's in the diagram here, is it?
Yeah.
I see. So the friction, okay, yeah, because yeah, normally we think of friction as let's say parallel to the surface. I mean, if the balls yeah, so now the friction is at some angle
Yeah.
from okay, wow. Yeah, yeah. Really, really impressive. I definitely have to say. Yeah. And okay, from symmetry, I mean in general, like you have N1 and N2 in this diagram, right? Would there be situations where N1 and N2 are different, or is that due to the rotation of the ball? Would that sort of like would that change the effect of the normal contact from the floor surface?
I think that could be possible. Also because like for each like all the balls interacting with each other could also mean that like the interactions from other balls, like other than these two, could also change the magnitudes of these forces. Because if you had multiple interactions and you have like because the frictional force points at an angle, so it could be changing the sort of vertical components of all the forces.
Right, 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 right. Okay, okay. So at every time step, uh so many interactions could be happening all at the same time. Wow, okay. Did you write your code in like Python or uh
Yeah, Python.
Python? Okay, cool, cool. Did you open source your code, by the way?
No.
Okay. Would be fascinating to take a look. I mean, yeah, probably take me several days to look through it, but yeah, cool, cool. Okay. Any other questions? I hope I pronounced your name correctly. Juhita, Juhita. Would you have any questions?
No, thank you.
Okay. Thanks so much. Okay. Wow. Yeah. Okay. The studies restricted the motions of the balls in a plane. Okay, my understanding is, of course, the forces are definitely not within the plane, but I think we assume that the center of mass of all the balls are always in the plane because they don't bounce around and so on. That's right, right? We don't, at least we don't, yeah, we don't consider collisions with the ground in that sense because they are all initialized to be sort of
Yeah.
on the ground. Yeah, and in between you won't get the balls bouncing up and so on in your simulation, right? And I guess experimentally that probably doesn't happen as well if you
Yeah.
because of the
Doesn't.
swirling. Yeah, I mean it's not so vigorous that sort of like random things happen like that. Okay, and so I also noted that experimentally you put a non-friction mat under your what was it petri dish was it
Mm.
uh uh Okay, and yeah, I guess that was sticky enough that you didn't have to sort of tape it down. Uh, yeah, okay, that's probably a not very critical point, but okay, yeah, very very fascinating. Any other questions from anyone else? Okay, let me try to think. Yeah, definitely lots of interesting ideas and things came up. Maybe if Vera, if you could go back a couple of slides from this current one, I think uh, I recall sort of having some questions just before you talk about Hertzian contact. Okay, this one, maybe one more before. Okay, maybe I'm just mistaken. Okay, because Joylyn has another question in the chat. How much force was used to move the balls in circular motion, and how was it kept constant? Okay, so I believe maybe Vera, if you could go to the slide that showed your experimental setup, that probably would be useful. So because this is probably the part that Joylyn also missed, part that showed the camera. Yeah, you put your phone and so on, right? Yes. Okay. So this is okay. So you called it what, an orbital shaker, right? So it's an
Yeah.
orbital shaker. It's got like basically a tape a horizontal kind of surface that goes round, 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 right? And then on top
Mm.
of that, she put a non-friction mat, right? Those kind you have in your car, to put stuff on. And then the petri dish goes on top, and then the steel balls go inside, and then you have, okay, the container outside is that to, I guess that's to put your phone on, right? That
Yeah.
box is really to just put your phone, right? Then the phone is there, and then the spirit level to make sure everything's horizontal. So back to Jolin's question, how much for? So what the only thing the only thing that is sort of the sort of independent variable really is the setting of this orbital shaker, right? You
Yeah.
can determine what's the frequency, like you have 10 revolutions per second, or 20 or 30, or so on. And then so then I guess that determines after that all the various forces, because there are so many forces on the ball. But yeah, the sort of theoretical analysis of it is that the that circular motion of the petri dish, right, is then analyzed as what we call it a non-inertial frame, where you put in your sort of apparent force, which is your centrifugal force, and you analyze everything from that rotating frame, right? To characterize how the balls move within that frame, within the petri dish, in other words. Yeah, so hope that answers your question. Darlene, do let us know if there are further questions like that about that. Okay, and Vera, when we see that the one, I know of course you can sort of color one of the balls blue. Is that the one that you sort of use your marker and sort of color it
Yeah.
blue? Okay, right, and that helps of course with the tracking lah. Yeah, generally when you do the tracking in these ones, you just choose one ball and track it. Do you actually try to track all? Wait, sometimes in some experiments, do you actually track every single ball?
Yeah,
Uh,
that one is also possible, but that one can be automated because I don't need to follow the path of a specific ball. So what I
okay.
do is like I basically binarize my video and then I use like a sort of ellipse fitter and then so I can identify each of the circular shapes.
I see, I see. Those are when they are co-rotating and you have all the concentric circles. I see. Cool. So I guess all in all, I mean, how long would you say, working on this project, how long did it take you really to get all the sort of data and experiments and all that? It must have been a whole lot of work.
So actually for this, like I took over this problem from someone else who had already done it at SYPT. So there was like I didn't really have to do much of my own research at that point because I already had some idea of the problem from that person and I just knew like what was the future work. So like for SYPT, it was around a period of maybe 3 or 4 months, which was a lot already. And at that point, the problem was still really, really incomplete. And then with OIPT, we started working on it, I think, in around maybe April. But I think most of the work was done in like June or later, and then like the actual OIPT was at the start of August, so it's really like on a span of like many, many months.
Wow, that's amazing. Yeah, really, really well done. I think it's really uh, amazing effort. Thanks so much.
Thank you.
Anyone else has any further questions for Vera? Right? If not, I think we'll all agree that we really learned a lot from her sharing this very interesting problem. I think it's not a simple one, uh, even though maybe it uses very geometric objects, right? Of course, identical balls, but so many parameters come into play. Changing the number of balls, changing the rotation rate, size of the ball, even the material of the ball. To really explore this whole space of all the interesting behavior is really amazing. And so please join me to also thank Vera once again. And Vera, really, really thank you very much for conducting this session for us. Okay, take care, everyone. This is actually our last Pi session for this year. If you'd like to have more of these webinars, just let us know. And it's really nice to really just spend an afternoon really discussing physics with all of you. Right. Thank you so much, Vera. It has been a real pleasure of mine. All right. Take care and all the best,
Thank
everyone,
you.
for the rest of term and rest of the year. Thank you so much.